Introductory Chemistry, Chapter 4, Atoms and Elements. So Dalton's atomic theory, which he worked on from 1803 to 1807, discusses the properties basically of an atom. And so his first theory, part of his theory, was that all matter consists of tiny particles called atoms. And we know that you cannot break atoms down any further, right? Once you try and break them down, they do not retain the same properties. An atom cannot be created, divided, destroyed, or converted to any other types of atoms. Well, there's a little star there because in chemistry, or I should say in chemical reactions, you can't do this. But in nuclear reactions, you can actually change one atom into another atom. But for all chemical reactions, what this means is if you start with a carbon atom, you have to end with a carbon atom. Atoms of a particular element have identical properties. So this means that they behave the same, chemical properties, physical properties. Now, there's a star here as well. This is because we can look at atoms in terms of their different isotopes, which means that they weigh different amounts, which would change their physical property. However, it does not change their chemical property. Atoms of different elements combine in simple whole number ratios to produce compounds. So you can take hydrogen and oxygen, you can combine them, 2 hydrogens for every 1 oxygen, you get water. You can also take 2 hydrogens with 2 oxygens, and that makes hydrogen peroxide. But these are always going to be fixed amounts. So if it is water, it has to be H2O. If it's hydrogen peroxide, it has to be H2O2. And remember that compounds are substances that have 2 different types of elements. So 2 different types of atoms that are bonded together. Chemical change involves joining, separating, or rearranging atoms. So any type of chemical reaction, you're breaking bonds and you're making new bonds. The nuclear theory of the atom. So the original hypothesis was basically that atoms looked kind of like chocolate chip cookies, where they thought that the protons were distributed evenly throughout the atom. So they designed an experiment, Ernest Rutherford did, and what he said was, I'm gonna set up a gold piece of foil, like aluminum foil, but with gold. We're gonna shoot out some alpha particles, which an alpha particle is a helium nucleus. So that means that there's 2 protons and 2 neutrons, but no electrons. So it's a fairly large particle. So we shoot the alpha particles at the gold foil. If this hypothesis was correct, then what we would expect is there should be some bouncing off of these protons that are distributed throughout the atom. Now, what was discovered was that most of the particles just went straight through. Some of them were deflected, some of them bounced back. So this original hypothesis was incorrect. If these little protons were throughout here, then we should have seen a lot more of the alpha particles just bouncing back. But instead they went through. So the actual result was that in the center of the nucleus, we have most of the mass of the atom. So here's where all of the protons sit. And then that the actual atom is mostly empty space. So that's why when the alpha particles were projected at the gold foil, most of them just went through. So what are the characteristics of atomic particles? Location. In the nucleus of the atom, you have your protons and your neutrons. Your electrons float around on the outside in their own little special orbitals. The charges. A proton is positive, an electron is negative, and a neutron is neutral. So for any given atom, it's going to start off with an equal number of protons and electrons. So that means that an atom will be neutral unless you add some electrons in or take some electrons away. If you change the number of protons, you actually change the identity of the atom. So the volume versus the density, right? So most of the atom is empty space, so the density is found mostly in the center, and the rest of it is just some electrons floating around. So electrical charge is a fundamental property. So that means you're either positive or you're negative or you're neutral. It's just how you exist. Particles that have the same charge are going to repel each other. So protons repel protons and electrons repel electrons. If you have a different charge, you are attracted to each other. So that means that protons and electrons feel an attractive force between each other. That's how an atom is able to hold on to its own electrons and also to attract electrons from a different atom. So once again, with our neutrality, your opposite charges are going to cancel each other out. So for every proton that you have, if you have an electron, then your overall charge would be 0. Keeping in mind that neutrons do not contribute any type of charge to an atom. So here's just a little table showing the basic breakdown of our properties of our subatomic particles and how we can represent them. So electrons have a little letter E, protons have a P, neutrons are an N. Your charge, electrons and protons are oppositely charged. The P for proton is positive, that's how we can remember that. Neutrons are 0, so they are neutral, and electrons are -1. Comparing masses, we can see here that the mass of a proton and neutron are effectively the same, and the mass of an electron is 10 to the -4th times smaller. So that means that it's basically 10,000 times smaller than a proton or a neutron. So really, really teeny tiny compared to the protons and neutrons. If we look at the actual mass in grams, we once again see this relationship where our protons and neutrons are effectively the same mass, and our electrons are 10,000 times smaller. So how was the periodic table developed? Well, Dmitri Mendeleev and Lother Meyer were two scientists working independently to develop basically our modern periodic table. Originally, when they were putting together the different elements, they thought that the organization of the chart should be based on mass, atomic mass, but they found that that was incorrect. Instead, they looked at what we call a periodic law, which means that every so often, the properties of an element are going to repeat themselves. So just like on a piano, right, you have your notes, and a C, if you go up another octave, it's still a C, but it sounds a little bit different, but it's all the same notes. So all the same C, right, C notes sound the same, they just might be higher or lower than the other. So the periodic law works the same way with elements. You go through typically about every 8, and you'll start to see that, hey, these elements behave similarly to what they're grouped with. So how can we classify our elements? So first thing we look at is a period, and a period is simply a row. So we look at period 1, period 2, 3, 4, 5, etc. Your group, which is also known as your family, are the different columns. And so here's where we see that group 1 elements behave the same, right? So we go through 1, 2, 3, 4, 5, 6, 7, 8. We start again. Lithium and sodium behave the same way that beryllium and magnesium do. So here's where our periodic law takes effect. The metals. So most elements that exist are metals. So all of the blue, this kind of teal color, the blue over here, those are all metals, as well as this light blue down here. The nonmetals are all listed in yellow. So there's much fewer nonmetals. And even though hydrogen is listed over here with the group 1 metals, it's truly a nonmetal, but it behaves in a way that is similar to the rest of the elements in this group. Our metalloids are these green elements that are here along this little stair step. So how do metals, nonmetals, and metalloids differ from each other? Well, metals typically conduct heat really well. They conduct electricity pretty well. Some are ductile, which means you can draw them out into wires. You can also pound them out into sheets of metal. Non-metals are the opposite, right? They don't tend to conduct electricity or heat very well. They exist in a multitude of states, gases, liquids, and solids, whereas most metals are solid at room temperature. And then your metalloids have properties in between metals and non-metals. So they're semiconductors. They somewhat conduct electricity, but not as well as a metal does. So our main group elements on our periodic table are labeled with the big letter A. So groups 1 and 2 over here, and then we hop over this middle pond and look to the elements over here. So your main group elements are 8 different groups. Our transition metals are what's in this pond here that I like to call, as well as down here. So we have our transition metals and then our inner transition metals. Furthermore, our group 1 metals, excluding hydrogen, right, because that's a non-metal, these are all called alkali metals. So alkaline batteries, right, lithium batteries, alkali metals. Group 2, alkaline earth metals. Then we go over here and look at group 7. Those are called halogens. And then we have our noble gases in group 8. These were once called inert gases because they thought that they never reacted with anything. But then some chemistry was done with fluorine, and with the bigger noble gases, it was shown that you could actually form some fluoride compounds with them. What's some information that we get from the periodic table? Well, we have our atomic number, and the atomic number is always listed at the top of the box. That tells us how many protons an element has. We have our elemental symbol, which is either going to be 1 letter or 2 letters, and the first letter will always be capitalized. Then we have the name listed at the bottom. So Ca is calcium. And then we have our atomic weight, which is 40.08. So if we look at 1 atom, we consider that to be in atomic mass units. If we have 1 mole of those atoms, then we would consider that to be in grams. So we don't change the number, it's just changing the unit. So if we pull out our periodic table, which you should either have a copy of, or if you just look in the front of your book, let's identify the group and the period to which each of the following belong. So P stands for phosphorus. If you look, it is found in group 5A. It is a main group element, and it is in period 3. So row 3, column 5. Chromium. Chromium is a transition metal. It is found in group 6B, and it is in row 4, period 4. Element 30. So element 30, we're looking at the atomic number, the number at the top of the box. That happens to be zinc, and it is in group 2B, and it is found in period 4. So how many total elements are found in period 6? So we count down our rows, find row 6, and we count across, keeping in mind that we jump down and we have to include those inner transition metals. And if we go all the way across, we will find that there are a total number of 32 elements in period 6. How many elements are in group 5A? So I look there. Once again, that's a main group element because it has that big letter A. And there are a total of 6 elements in that family, right? Group and family mean the same thing. So something that an atom can do is either gain or lose electrons. And when it does that, it becomes an ion. And an ion is something that is just, it has a charge associated with it. So it's either positive or negative. So the positively charged ion we call a cation. And the way that we remember that is the T in cation looks like a positive sign. So it is a positively charged element, atom. How does it become positively charged? Well, it's going to lose an electron. So that means an electron is written as a product, right? Reactants to the left, products to the right. So sodium happens to lose 1 electron to become sodium plus 1. Now, if you look at group 1, you'll see that all of the elements in group 1 become a positive 1 charge. That is because they belong to the same family, so they behave similarly. Typically, cations are metals. Metals like to lose electrons to become more stable. So just the opposite of a cation is an anion. How do we remember this? Well, the anion is a negative ion. So the N stands for negative, where up here we said the T looks like a positive charge. So anions are negative. Why? Because they're gaining so many electrons. However many electrons they gain, that becomes its charge. So fluorine is a halogen, group 7. It likes to gain an electron to become F with a -1 charge. Notice all of the halogens behave similarly. With your main group elements, if we look down here, depending upon what group you're in, it's going to tell you the charge that it takes. So group 1 metals like to be +1. Group 2 metals like to be +2. Group 3 metals like to be +3. Now, when we get into group 4, we have a nonmetal, we have some semi-metals or metalloids, and then we have metals at the bottom. So our metals down here, they're a group 4. They like to be a +4, but they can also become a +2. Carbon is a nonmetal. Carbon can take on different charges. It's its own special branch of chemistry called organic chemistry, and more often than not, it's going to form covalent bonds where it's not going to take a charge, but instead it's just going to share its electrons in different ways. Group 5, now what we look at is our nonmetals, right, are becoming anions, negatively charged. So if we take and we subtract away 8, 5 minus 8 gives us a -3. Group 6 nonmetals like to become a -2 because 6 minus 8 is -2. And then your group 7, 7 minus 8 is a -1. So our nonmetals like to become negative, our metals like to become positive, and in this middle here where our transition elements are, they're called transition elements because they can lose different numbers of electrons. So we can end up with +2 or +3 for chromium, manganese, iron, cobalt, and nickel. Copper's +1 or 2, silver's a +1, gold is +1 or +3. These are a little harder to remember because they aren't a main group element, so they don't always follow one certain rule. Zinc likes to be +2, cadmium likes to be +2, and then mercury does some special things where it's a diatomic molecule with a +2 or a monoatomic with a +2. So the important thing with this is to keep in mind, cations are positive, anions are negative. Cations are losing electrons, anions are gaining electrons. So how can we symbolically represent an element? Well, our big letter X here is just going to be your elemental symbol. So H for hydrogen, He for helium, Cl for chlorine. At the top right, a superscript, right? Superscripts are at the top, subscripts would be at the bottom. This is where a charge would be located. If there's nothing there, then the charge is 0, how most elements start because they have an equal number of protons and electrons. Now, to the left of our elemental symbol, at the top, we can be given a mass number. Your mass number is going to tell you the total number of protons and neutrons for a given nucleus. And then at the bottom, which is a subscript, we have the letter Z, which represents the atomic number. The atomic number can be found on the periodic table, and it tells you the number of protons. Sometimes this number may not be given. However, if we know the elemental symbol, then we automatically know the atomic number because there's only one atomic number for each element. You change the atomic number, you change the element. Now, the mass number has to be a number that is given to you. You cannot guess at it. It has to be provided. So what are some equations that we can use to determine how many protons, electrons, and neutrons something has? So if you have a mass number, you simply take your protons, add them to your neutrons. That's how we get that number. As stated, your number of protons is the atomic number. So you can always know the atomic number because that's listed on the periodic table. If you want to know how many neutrons you have, you subtract your atomic number from your mass number. If you want to know the number of electrons that you have, it is simply equal to the number of protons if the overall charge on the atom is neutral. Remember, most atoms are neutral. The only way they aren't neutral is if there's a charge that is shown at the top right-hand corner of that element, the elemental symbol. So then, if you want to know the charge of something, you take the number of protons and you subtract the number of electrons. So looking at these two elements, let's determine how many protons, neutrons, and electrons there are. So boron, remember, this is the atomic number. If it wasn't given, we just look on our periodic table. The number at the top is our mass number. So I know by looking at this that boron has 5 protons. There's no charge, which means there's also 5 electrons. Then I can just subtract 11 minus 5 equals 6, and that tells me the number of neutrons. So boron has 5 protons, 5 electrons, and 6 neutrons. Same thing for iron. So iron is element number 26. The 26 tells us the number of protons. Also, because there's no charge, it tells us the number of electrons. Those numbers are the same. This is our mass number. So this tells us the total number of protons and neutrons. So if we subtract 55 minus 26, we see that there are 29 neutrons. So iron has 26 protons, 26 electrons, and 29 neutrons. So isotopes are looking at the same element. It just has a different number of neutrons. So basically the only thing that changes is the mass number. So going back to slide 1 where we were talking about Dalton's atomic theory of matter, this is where his original theory wasn't entirely correct because this is a different physical property. The mass of something is a physical property. So if you weigh different, that's obviously makes you different. So there's 3 different isotopes of hydrogen. We have our normal hydrogen, which has no neutrons. So hydrogen has an atomic number of 1, which means that there is 1 proton. Each hydrogen atom has to have 1 proton. If it has a different number of protons, it's a different atom. So here now we have hydrogen 2, which we call deuterium, also known as heavy hydrogen, or you can make heavy water with that. So now we have 1 proton and 1 neutron. And then we have tritium, which is hydrogen 3. So we still have our 1 proton, but now we have 2 neutrons. So basically for all the different elements, you have different isotopes that occur naturally in nature. And looking at all of those together is how we can determine the actual atomic mass for a particular atom. These hydrogen atoms, regardless of their mass, still behave the same chemically. So it doesn't matter whether you have deuterium or tritium or plain old hydrogen, it's still going to react the same way. Chemical properties are the same for isotopes. Their physical property is different. Oh, I was just saying this. So we have identical chemical properties, which means that the isotopes react in chemical reactions in the same manner. Some isotopes, however, are radioactive. This is both good and bad because there are certain isotopes that we can use in medicine to help trace through the body to identify when certain organs or glands are not working properly. So let's look at the periodic table. What is the atomic number of chlorine? I find chlorine, it is a halogen, which means it's group 7. The top number that is given is its atomic number. That's 17. What does that tell me? That chlorine has 17 protons. If it's neutral, it has 17 electrons. What is the mass that is given? When you look underneath, you see that it's 35.45. This is not the mass number of an isotope. Remember, the mass number has to be given. When I look at this 35.45, this is a fraction, and you can't have a half of a proton or a half of a neutron. That does not exist. You either are or you aren't. You exist or you don't. You have that neutron or you don't. So this 35.45 is considered its atomic mass, and this is what we call a weighted average. So the different types of isotopes for chlorine are chlorine 35 and chlorine 37. So in nature, you either have chlorine 35, which means you have 18 neutrons, or you have chlorine 37, which means you have 20 neutrons. That's it. So they exist in a percent abundance that says it's a 3-to-1 ratio, which means 75% of all the chlorine atoms are chlorine 35. 25% are chlorine 37. If we do some math, which I'll show you how to do, we can come up then with this number of 35.45. That is what we call the weighted average. So you take a look at all the naturally occurring isotopes, the percentage with which they exist, and then you're going to multiply those numbers together and add them up. And this is how we get to the atomic masses on the periodic table. So you can find an atomic number and you can find an atomic mass on the periodic table. What you cannot find on the periodic table is the mass number, which tells you exactly for each element, how many neutrons do you have. Those are different. But we just look at what's the average mass of a particular element. So how do we do this? Well, we have some more exact percentages here that say chlorine 35 is 75.77%, and chlorine 37 is 24.23%. So we convert the percentages to a decimal fraction, which just means that we're going to move the decimal point over 2 places. 24.23 divided by 100. 75.77 divided by 100. That's how we get these two numbers. Now you take the percentage that we converted into a decimal and multiply it by the mass that it belongs with. So 0.7577 times 35 gives us 26.52. Then we take 0.2423 times 37, 0.00, and that equals 8.965. When you add these two numbers together, we get the approximate mass of chlorine, which is 35.49. So this is how you do this. And when we talk about averages, oftentimes we'll think we're going to add numbers together and divide by 2. That would only work if we had 50% abundance of each of 2 types of isotopes, which typically don't exist. So once again, these numbers can be found on the periodic table, but you cannot use them to determine the number of neutrons.